Mason with what's next for Transducers.jl. Please take it away.
Thanks. Okay, so Transducers.jl is a package that was written by Takafumi Arakaki, and it's based off a concept that was developed for the Clojure language by Rich Hickey. I'm not either of these people, but I've been trying to maintain Transducers.jl, and I want to talk a bit today about kind of how Transducers works under the hood, what the actual mechanism is here that's novel, and then kind of what sort of challenges I've been facing while trying to maintain it, and then what I would like to have done in the future. So the basic idea here is that lots of programs that we like to write, especially loopy ones, can be described as some sort of process where we take in some collection of data, we do something with these chunks of data, and we produce some result. And often, almost always, when we're doing this, we're conflating a few different things. So what type of container is actually holding my pieces of data? What am I trying to do to that data? And how is it being scheduled? Like, am I doing some sort of sequential loop? Am I trying to do some sort of SIMD thing, distributed, threading, GPU sort of thing? These things are often all kind of mushed together in people's code. And transducers is one kind of interesting idea for how to disentangle these three things, and with a goal towards kind of letting users focus on what they want to do with their data, and just write one transducer that describes what they want to do, and then reuse that transducer for a vector, a tuple, a channel, whatever, and have many different execution models that the transducers library would focus on. So we can, at the library level, we can focus on being very generic with having backends for sequential, threaded, GPU sort of backends. So, okay, before I talk about transducers, I want to introduce a bit of background. So reductions is one of these kind of scary comp sci things that people start trying to describe and everyone's eyes glaze over, so I'll give it a shot. We have this function in Julia called foldL, and this is really just, at the end of the day, a kind of structured way of describing a loop. So when I say foldL with this function op, this gets lowered into basically initializing some sort of state, looping over my collection x's, and at each step of this loop, I want to update my state by applying this operator to the previous state and the element. And then I just return the final state. So this is a very generic process that can describe pretty much any loop, depending on what op is, right? And Julia also has this function reduce, which is for the cases where you don't care about the order, or really the associativity. So if you don't care if I go forwards through the loop, or backwards through the loop, or pairwise through the loop, then typically you want to use reduce, because then Julia is free to choose like some sort of pairwise scheme that maybe reduces error or something like that. And this is very abstract, but I think almost everyone in this room should be familiar with at least two reductions, which are sum and prod. Sum is just reduce with plus, so you add up every element in a list, and prod is just multiplying together every element in the list. And so you can kind of go from there and build up an intuition for how these things should work. And then this is just a little diagram showing like this is how you kind of contract together elements with foldL, and with reduce you might do some sort of pairwise thing like this. And this is why reduce is parallelizable, basically, that you can do this reduction at the same time as you do this reduction, and then you combine them at the end. And these two things will be equal if this function op is associative. The other bit of background I want to describe quickly is iterators. So we have these things in Julia called iterators, and this is kind of the typical way of describing some sort of lazy transformation over data. So you wrap some sort of collection with the iterator, and then the iterator redefines what it means to take elements out of that wrapped collection. So, like as an example, we can define like a filter over the range 1 to 10, where we filter out for the even elements. And if we write some loop over this iterator, we see that the loop only sees these even elements, 1, 2, 4, 6, 8, 10. The reason this works is that Julia's loops really just desugar to something that calls this iterate function on the elements, and then it just keeps on going in a while loop until iterate returns nothing, and then it finishes. So these iterators are state machines, and they use this function based out iterate to pull values through some chain of nested iterators. And this whole process is kind of essentially inherently sequential, and it can often be inefficient. There's ways around these inefficiencies, but it kind of requires some gymnastics and a lot of knowledge of this deeply nested structure to make efficient. So as an example of how these things can be inefficient, if you want to add up, say I have some filter over the even numbers in some collection, and then I want to double each of those filtered results. What a standard implementation of fold-L would end up doing is this kind of double while loop, where you get stuck in the first while loop, and then you fall into this inner while loop, and you keep on iterating until you get an even number, then you break out of that while loop, you double things, you add them up, and then you go back into the inner while loop, which is probably not what you would intuitively write, but maybe a sufficiently smart compiler will fix it, blah, blah, blah. With transducers, we instead of defining these map or filter things that act on data, we have these uppercase map and filter transducers that really end up transforming reducing functions. So what using these things kind of looks like is you might use this fold XL function that comes out of transducers. And this thing is basically describing some way to transform this plus. So you can also write this alternatively in this kind of pipeline fashion. So you say 1 to 10, filter is even, and then sum up. That's another way of writing this. And you can also compose transducers with this syntax I'm maybe not the biggest fan of, but I'm going to kind of focus on this kind of a bit more verbose syntax here instead of the pipeline syntax, because for the purposes of this talk, it's a bit more clear as to what's going on. So, and also, you don't really necessarily need to use this floops, all this syntax, because we have packages like floops.jl for using for loop syntax, if that's what you prefer. But anyways, what's going on kind of under the hood here, and what makes this different from an iterator, is that we're actually not transforming the data, but we're transforming the functions. So when I try and apply this transducer XF to some fold, I create new reducing operators. So first, we apply this isEven transducer to my reducing operator plus. And this creates a new reducing operator. I'm calling RF prime here, that takes, and this is just a 2-argument function that takes some state and some element. This is the body of the while loop, or the for loop. And it just checks, is x even? If so, I'm going to apply this reducing operator, in this case plus, to add the state to x. If it's not even, I just return the state. The state is unchanged, right? Because I'm filtering out this thing, so I don't want to change the state. And then we can apply the map transducer to this transformed reducing function. And instead of acting on the outside, this actually goes to the inside. So I still check is even, but I'm going to now add state to double x. So, and the way we're kind of able to operate from the outside in here is that these transducer objects, so if I take map and then apply filter to it and then apply all that to plus, I get this kind of structured object that's a reduction map of a reduction filter of a reduction plus. And yeah, this is just a structured thing the transducers library is able to take advantage of for various things. But and so basically what ends up happening here is that if we compare that to the code generated by the iterator sum of the filtered loop, we get something that's much more like what you would actually want to write or what you would think to write by hand. Now it turns out that Julia, if you try this, Julia will actually generate this code, but that's because Takafumi submitted a PR that detects filter map and then makes it do this one instead of the other one. But a naive implementation of FoldL would do this. And what's nice is that we can, if you use transducers, you can just do this with function composition instead of hoping that your compiler detects that, oh, if you have a double while loop with a break, then that's actually an if statement and blah, blah, blah. Okay. So the other thing that's really nice about these transducers is that because they're just functions, we can apply them kind of wherever we want with whatever schedulers we want. So here's, the filter is even with map that's going to tell me, okay, I had some element I on some thread ID. So if I put this in fold XL, we get what we expect. We get 2, 4, 6, 8, 10, all on thread 1. But there's also this fold XT, T for thread or task or whatever. And if we use that as our kind of scheduler here, we get 6, 8, 4, 2, 10 on thread 2, 3, 5, 4, 1. So this is easily multi-threaded. And it turns out that you can also use a distributed scheduler, so fold XD for distributed, and we get worker 6, worker 4, worker 2, worker 5, all kind of sufficiently out of order. So using these reducing function transforms, instead of we kind of decouple from the data and we let schedulers worry about scheduling, we get users worry about what my actual function is. And in some ways it's kind of similar but different to the ideas in these kernel transforms as well. But yeah, and we also have, there used to be a GPU like a CUDA plugin that could compile these things to GPUs. It's not currently working. Hopefully we can get that working in the near future. And yeah, one of the other advantages of these things is that these transducers can kind of define traits on themselves that tell you information about what they do. So we have transducers that, like map, is a size-preserving transducer. So if you just have map and I don't know, like enumerate or something, then you know that whatever collection comes out of that series of transducers will be the same length as the collection that went in. So if you're doing a collect, you can pre-allocate an output that's of the appropriate size. If you have map and filter, then we know that the collection is going to be smaller than the original collection. If you have map and map splat or something, or map cat, then it might be larger than the incoming collection. And also, we know that some transducers carry state, like enumerate. And so if you have a stateful transducer, then you know, okay, I can tell the user right away, that's not parallelizable. I can't put that on fold XT. So unfortunately, not everything is sunshine and rainbows in transducers land. So there's kind of a whole ecosystem around these transducers packages, and they all only had one maintainer. And when that maintainer kind of disappeared, which is something that happens in open source, there was a whole constellation of packages that were kind of suddenly orphaned and had couldn't receive updates, and didn't really have anyone to give them updates. So I eventually have been taking over these packages one by one as they need updates, moving them over to a new organization, and reworking everything to get them running again and accept patches. So thanks. Well, so I don't pat me on the back too much because I haven't been doing that great a job of it. But one thing that's quite nice about this is that even though on the logistical side it's quite a pain, PKG, like our package manager, makes this seamless for users. Users can just say update transducers, and they'll get the new version from the new repos. But if you do find yourself maintaining a important package on your own, please consider giving shared ownership to at least one other person, so that if you suddenly disappear for whatever reason, other people can continue your work. So the other kind of major problem, other than all these logistical challenges, is just that the code base itself is quite large and quite complicated, and it evolved a lot over time. So a lot of this was written in Julia 1.0, and there's all sorts of tricks for avoiding the fact that we used to have allocations from having a mutable struct inside an immutable struct and stuff like this, and so there's a bunch of tricks that might not even be needed anymore. But then there's also things that definitely are needed still, and if I remove them, stuff breaks and stuff like that. So I've been having a lot of challenges trying to understand what to do, like how to fix things in this code base. So I'm currently working on better understanding all these internal mechanisms. I was hoping I would be able to show off a bit this simple transducers package I've been writing, but it's not currently in that sort of state. I haven't had as much time as I had hoped. But the idea here is this might end up being kind of the future of transducers, or it might be kind of just a project that I use to better understand, okay, how do all these mechanisms really work? I can go through line by line in the original transducers and see, is this something that's necessary for like a simple version of this package? Move that over if it is. If it's not, just leave it. And I can also hopefully use this as a learning tool, because I've had a lot of people come to me and be like, hey, I'd like to help out, but like, I don't understand what's going on in this package, and I don't understand either, so I can't really teach them. So hopefully with a simple transducers package, I can show people that and have that as a bit of an onboarding experience for people. The other thing is that the APIs kind of grew organically, so like we have foldXL, foldXT, foldXD for thread or sequential threads and distributed, but then if you want to do it on the GPU with the broken GPU package, it was an executor interface and you had to do something else. And so I'd like to start kind of unifying some of these things, fixed naming, stuff like that. There was also another package that maybe would have been a better idea to present here, which is Oh My Threads. And we learned a lot of performance lessons. So this package was heavily inspired by transducers, but then we learned a bunch of lessons while implementing it that I think can speed up a lot of certain multi-threaded tasks in transducers. So I'd like to bring some of those lessons from Oh My Threads into transducers. And then, yeah, I'd really like to get this folds CUDA thing working again, because it's always nice to be able to run things on GPUs. And finally, I'd like to put it out there that if you think this sort of stuff is interesting and this is something you'd like to help out with, it doesn't need to be a big job, but reach out to me. Maybe I can try and find something that I could get you started on. So yeah, that's it for me.
Thank you. Any questions already? I see multiple hands. Nice.
Hi, thanks. I was wondering, this dream of back-end agnostic execution reminds me a lot of Dagger, which we learned about at the beginning of the week. Is there any collaboration or interactions going on there? And if not, why not?
Yeah, so I think Dagger is actually a great candidate for kind of getting plugged into this whole transducers world for a couple reasons. One, it'd be nice for transducers to be able to, so I think we already have a OK scheduler, but I think Dagger has a much better schedule for distributed stuff, so I'd like to use that. But also, I was talking to Julian about this, and he really wants users to be able to write a for loop as well. And with transducers, we have this floops package that can turn some complicated series of for loops, even with continue and break, and it can turn that into a series of transducers. And so if we get a executor for Dagger working with transducers, then I think that's something that both sides would benefit from. And it's something Julian's interested in, it's something I'm interested in. So hopefully that can happen in the near future.
in the graphs world, there's been this like light graphs package, then then became the new graphs package. Is this how you also imagine simple transducers?
Probably not. I'm hoping that, so it kind of depends, I guess. So one of the things that makes me kind of want to focus on simple transducers right now is that Transducers.jl has like 20 different transducers it defines, like map, filter, has all these very complicated ones, and I don't really want to think about most of them. I just want to think about like a small subset of them and a small subset of foldables. But I'm hoping that depending on how things go, I can just start learning lessons in this simple package and then bringing them to the more complicated one and keep the simple one as a learning tool for people or something. But it might end up being preferable to just move forward with the simple one.
Okay, but like maybe ideally simple transducers will never be the package that people are recommended to use primarily.
I don't know yet, but probably not, but it's certainly possible.
All right, thank you.
Is there a chance for false kernel abstraction?
Yeah. Actually, yeah, I guess, so I think when Folds CUDA was written, Folds kernel abstraction was, kernel abstraction might not have existed or was quite immature. So probably if I have to do a full rewrite of Folds CUDA, it would be a Folds kernel abstraction, but might be able to just fix a couple low-lying things and get Folds CUDA going, so maybe that's the way to go in the near future, but definitely interest.
So this is kind of a follow-up question. So does the Folds CUDA breaks because they are just because like the maintenance issue, or there are some kind of a technical issue like cannot be solved right now?
Folds CUDA was never mature. It was always kind of in the early stages. I think he started it not long before Takafumi disappeared. So there's probably some of that, and I think also that CUDA has made some breaking changes and stuff like that. Like I think CUDA was not on as firm footing back then as it is today, and so I don't actually fully understand what broke, but I assume it's just some classic bit rot where, oh, we made a non-breaking change, but like everything broke or something. I don't know, but we'll see. I think there was a question in the back, or okay.
Yeah, maybe not so relevant anymore, but I was curious about Folds.jl, which is, I guess, can you comment a little bit on it? It's a subset of transducers, I guess, or built on transducers,
yeah.
But I guess shares the same issues with, in terms of maintenance and so on.
So Folds.jl is basically, I don't know what happened to my thing, but it doesn't really matter, I guess. Folds.jl basically just tries to give people, instead of having to use this fold X whatever and a transducer, we just give them, folds.map, folds.sum, folds.reduce, and it will lower the transducers under the hood. We have ported Julia Folds or folds.jl to the new organization and want to keep supporting it. So for people that prefer the folds interface to the transducers interface, yeah, it shouldn't be too hard to keep alive. And yeah, we'll just keep on working on it as long as I can find time and people are interested.
So you mentioned about the traits. So for example, you mentioned like maps has a fixed length kind of. How is that implemented?
It's just dispatch. So I think basically there's just a function that's defined as like is size conserving, and then the method on map is it says size conserving. Yeah.
I wanted to ask, why did you take over Transducer's ecosystem? Like, very grateful that you are, very happy about this, but I kind of wanted to know what's your motivation?
Yeah, so I think I just kind of so it's maybe not quite as relevant today, but I think definitely when this whole transition was happening, there was no package I could recommend to people other than like the transducers based stuff if they just wanted to do multi-threading over some array, right? Like multi-threaded sum, multi-threaded for each or whatever. Base.threads has some great primitives. It is not a good end user experience. So that was one of the main motivations. And I also just find transducers to be a very interesting idea that I think hasn't been fully explored. And I would hate to see all this really brilliant work that Takafumi did. I would hate to see that go away. So I kind of just wanted to keep it going.